welcome everybody to Lecture 3, Information Retrieval in the summer semester 22-23. Weather got warmer again. I was very surprised when I left the house this morning. So can you please listen? Thank you. I will say something about your experiences with a 2 exercise sheet. You had 2 weeks to work on that. And then today's lecture is about efficiency, and we will see all about that. Here's the summary. And the exercise sheet will be a mathematical one. In particular, you will learn something about a technique called Lagrange Multipliers, and you have to apply that to a new algorithm, which you will learn today. But let's first start with the organizational stuff, experiences with the last exercise sheet. Most of you found it interesting. You learned a lot. It was quite time consuming, but you had 2 weeks for it. There were many small problems as usual, I think, because it was a bit more coding, and some of you had difficulties understanding the doc tests. Here a few quotes. So some of you really liked it. I had a great time. I've lost track of time, too many little problems. Mixed experience, first fun, then trouble. Yeah, the tests were, can you please listen? The tests were, yeah, it was not so easy to pass the tests, right? Because if you make even the tiniest of mistakes, then, but that's what unit tests are for. I think you made an important experience, namely when you have even a medium-sized, I mean, I would call it a small project, what you did for exercise sheet 2. If you don't have unit tests, then your code is not correct. I mean, it's almost 100%. I think was anybody here where you wrote your program, you ran it through for the first time, and then all the tests passed 100% without? Yes, there's someone. Perfect. Okay, so there are few exceptions, but usually, and when that is not the case and you don't have tests, it means, okay, works fine, you think it works fine, but there are small mistakes. Okay, very interesting and challenging. More hints on how to use the functions. So, yeah, Natalie will talk, and I will talk about that for the next sheets. The next sheet is mathematical. I think what you're saying is that some of you had trouble understanding from the doc test exactly what the functions were supposed to return, and that is maybe due to not fully understanding how Python doc tests work. So we try to give more explanations there. And that was a similar comment. Very productive, and somebody doesn't watch movies, likes books, okay. So, the results, so it was about tuning. I think it was a very important experience. You have the theory, and now you try to make it work for an actual application and search engine. Let's maybe also look at the table. So here's the table, what you did. So you tried all kind of things, playing around with the parameters. You had a training and a test set, trying all kinds of methods. And I think, one thing you experienced is you change a little bit. It makes a rather big difference. Also one experience is that you have an idea, it sounds good, but it actually makes it worse. So these are typical and valuable experiences. Most of you, I think, found that if you, the B, which is responsible for the weighting of the document length, if you make that smaller or even 0, gave better results. This was what we started with, the baseline from Natalie. Of course, there was room for improvement. These were the best results. What you also see, also interesting, so mean average precision. That's a mean value because it's very hard to get good, very far from 100%, and this is typical. 61% is even a pretty good value, so it's really high. You don't get perfect numbers, but that's just how it is. That's realistic. It's really hard to get a perfect ranking, even for such a toy collection and small benchmark. So yeah, super important, but also super hard. And it's hard to understand what's going on. Some of you took it as a learning experience. Some of you found it a bit annoying, but that's also part of this kind of research. The same when you do anything in machine learning. It's a lot of tweaking, trying to understand what's happening. It's of course very hard to understand and also to predict what's happening. Okay. Yeah, some of your favorite movies here. So if you, I will just show it, it's on the slides. If you want inspiration for watching new movies, especially movies which are maybe not so well known, but still very good. So here the highest down on the list at rank 24,276, an anime film. Here you have a list of recommendations. Okay, I think that's it for the introductory part. We have a full program today, so let's just continue unless you have some questions about exercise sheet 2 or about the organizational part. You can also write something in the chat anytime. Also the people in the room can write something in the chat. And the people at Zoom can also just talk and ask questions. Okay, then let's start. First, recap and motivation for this lecture. So we talked about list intersection already in lecture 1. And then in lecture 2, we have merged the lists. When you talk, I can hear you. I think you have to be, it's too loud otherwise, thank you. So intersection means you type keywords and then all the keywords must occur in your matching documents. We found in the second lecture that it's a good idea to do merging, which means, and use scores, which means not all scores, not all keywords have to occur. So both modes are relevant and used in real search engines. And it's also basic operation in database engines. That's called a join. Most of you, I guess, have heard some database lecture, and when you join two tables on some column or even several columns, these columns are usually sorted, or you can sort them, and then the join operation, joining two tables into one, it's also exactly a list intersect or merge, depending on whether you want an inner join, only the parts of the table where the columns match, or an outer join, also things where only one table matches. And we will actually come back to that in lecture 12. And I'm just writing that here to say that this is not a random routine we are looking at here, and today we have a whole lecture about it, but it's really a very important and central routine, intersecting or merging sorted lists of integers. It's central for efficiency of every search engine or database engine, so very fundamental. And today we will go back to intersection, so not merging, just for the sake of focus, and it's about efficient list intersection. We will start with some coding to give you some motivation, and also because it's quite fascinating, I think, what you will see. So stay buckle up. We will run code and measure it. So I just wanted to say something, because you will do this a lot in your future career, but also in the course of this lecture. Time measurement is actually not so easy because there is variation. You run it again, then it takes twice as long. What's happening? I mean, there are other jobs running on your machine. You have stuff like the garbage collector in Python. Also in Java, it's run, it doesn't run, it changes your runtime. Which part of the data is in which cache? We will not talk about that much today, but it's a big topic. There are all these caches. Data read from disk can be cached in main memory. There's this L1 cache, which is very fast access to a very small memory for things you're using all the time. TLB is something about virtual memory management. This also makes a big difference. We will do something very simple today. We will just repeat each measurement 3 times so that we at least see if there is a certain variation. So we're not computing any averages, just repeating 3 times. Of course, interestingly, if you repeat something 3 times, that can also distort the truth, because you're doing the same thing 3 times in a row. Then by doing it the first time, now all kinds of things are in the cache, and now the second and third time might be faster because of that, but unrealistically faster. So by trying to avoid problems and repeating it, you are again creating problems. But yeah, this is just a side note, so time measurement, if you want to do it scientifically correct and so that it actually says something, it's quite hard. Most of the lecture today will be about a new algorithm, which you haven't seen so far. So far we have had the zipper algorithm, which is this very simple linear time algorithm, zipper, because it's like a zipper. You go through the two lists in an interleaving fashion, so if they are very similar, it will actually interleave, so like a zipper. And before we go to the more complicated algorithm, let's just look at, you take one basic algorithm, even a simple one, and now you try all kinds of tricks. And what kind of tricks will we try? All kinds of variations in the implementation and the algorithm. You will see in a second. But it's still all zipper. What difference does it make? How do you store the lists? So in Python there is list, array, numpy arrays, and so on. In other programming languages you also have different data structures for how to store arrays or lists. Just implementing, not changing the implementation, but just minor tweaks in the implementation. Let's try different compilers. There's, who knows PyPy in the room? PyPy, do you know PyPy? Instead of Python, you only know it a little bit, which is why you show me. Okay, you also know it a little bit. Okay, we will also look at another programming languages. So we will just look at a lot of variation for one and the same basic algorithm. And let's just see which bandwidth of running time do we get. So we will see all kinds of codes doing the same thing with the same algorithm. What do you think the range of running times will be? What's the largest difference? Like the fastest program we have in the end and the slowest one, what will be the factor? 2, 5, 10, what do you think? You can also write it in the chat, just a guess. So like everybody in the code implements the same thing, and then we look at the slowest code and the fastest code. What do you think the factor will be between the 1,000? 1,000? That's a lot, right? Let's see. 1,000. Somebody said 1,000. That's yeah, 1,000 is a lot. It's maybe a bit unrealistic. So let's start with small variations in the running time. So I've prepared, because we also have other stuff, I've prepared something. Namely, I've prepared the code which does the list creation and the timing. And you see it here. Let's just go through it very quickly. It just creates, it's in Python. Let's start with Python. It creates two lists of a given size. So this is how I'm intending to use it, intersect timing.py. And let's start with two lists of different sizes. So maybe one is of size 1,000 and the other is of size 1,000,000. And then I have a fourth or third parameter, depending on how you count, which just says which variation will I use. I will call my algorithms intersect 1, intersect 2, intersect 3. So this, I guess, will not work because I've not implemented anything yet. And what will it do? It will just create two random lists. So the numbers are not from infinite range, but it's integers from a range which is just the size of the sum of the two lists, so that I have quite a bit of intersection, but also numbers which are different. First list is of size n1, the first is of size n2, so here it's 10,000 and 1,000,000, and then I just repeat it 3 times and time it, and I output the time in milliseconds, and also the size of the list, just as a very simple check whether they're actually doing the right thing. We should always get the same result size. And let's just, to warm up, start by implementing the standard zipper in some obvious way, maybe. So we had these two. This is basically what you did for exercise sheet 1. Just intersect, and and you tell me if I'm doing something wrong as usual. So ideally, when I'm finished with your comments, it runs. So what do? We run this because it's intersect. We run when we are at the end, as long as neither of the two lists is at its end. So we have this, right? As long as this list is not at its end and this list is not at its end. Okay, and now we check if the first list, so they are in a sorted order, ascending, so smallest number first. We are now at one position in list A, at another position in list B. We are comparing the two elements and we are checking which one is smaller. Let's say we are smaller in list A, and then we just proceed in list A, and we don't output anything. And if we are, maybe now we are at the end of list A, and then let's just break. Okay, and now let's do the same thing for B. So if Bj is less than AI, that's the other direction, then we proceed in this list. And if we now happen to be at the end of this list, then we break. And now let's check if they are actually equal. If AI is equal to Bj, and then we actually, what is it? Append. I always forget. Is it append for Python? Yes, thank you. Which one do we append? Intersect either of them because they are equal. And then we proceed in both lists. Set and little detail here, and then we return R. What are we actually doing when we have an element multiple times here? I want to ignore that detail basically. So what this does is, if we have it, I hear you talking, thank you. If I have it 2 times in one list, like 3, 3, 3, 3, and in the other list I have 3, 3, 3, what this code does, it will output it 2 times, so the minimum of the number of occurrences. That's just the semantics we're implementing here. Unclear what we want, let's just do it that way. Is this correct? Is this correct implementation of Zipper? What do you think? That's our first one. Yeah? No?
I personally don't have the quality checks with breaks and reports, so
Okay.
this could break something.
I mean, we need this, right? If we don't do this,
it cannot be equal to that because, sorry, if the condition you've given there, I is equal to that A.
can you give me a line number?
Line number 28.
28?
It can't go inside that because you've given y is I less than length A of A.
Now I'm confused. Why can't this happen? So this condition can be true, then I is increased. Now I may be at the end. What am I getting wrong?
I think the confusion comes from not using elif, because I think a lot of people implement elif, and then
Yeah, we will use that in our second iteration, else if. The first question is this wrong or is it just clumsy? What's your claim? Yeah, that's okay. Okay, that's deliberate. I wanted to start with, you just write your first version and, okay. Is anybody claiming that it's wrong or do you see a mistake? Okay, let's just try it for now. Let's first, there is a doc test here which just checks it for a simple list. Let's just run it, and the doc test intersect timing.py. Okay, it works. So it works. Doc test with 9 elements. It works. That's and let's just see the timing now, and then we see what. Okay, 200 milliseconds for intersecting 10,000 with 1 million. Okay, so I heard talk about elif. Let's just copy this now, and we will do this 4 times. We will write. So this is now intersect 2. We have to take care that we also intersect 2. So this is a variant with less ifs and more elifs Okay, that's what some of you suggested. So let's just, that's now quickly. Actually, if this, I think maybe I shouldn't delete this. We do this, else, if A is not smaller, now we know B is equal or larger, so let's just do this, then we don't have to do this. And otherwise, actually we know, otherwise we know that we are in the equal case, right? So either A is smaller, then we increase I, or B is smaller, then we increase J, or neither this nor that, then it's the equal case, and then we do this. Is this correct? I mean, that's now a little less clumsy. I think that's what you were getting at. Let's maybe run the doc test. Yeah, we have to make sure that we write 2. If we write 1 here, then in the doc test for 2, we just check 1 again. Okay, let's see. Difference in timing. 1, 2. Oh, okay. Surprise. So, what did we do wrong? I'm surprised. Actually, I was expecting it to be faster, but maybe you see a problem and we just
I think it's possible that in the first period it was breaking earlier.
say it again.
It doesn't go through a lot of while loops in the first period. It breaks earlier because of your its multiplier.
So where does it break? So what do you suggest to make it faster? Yeah, but it's interesting, right? You all said it's clumsy, we made a change and now it's slower. It's actually part of...
Maybe we could change the end to an or and ask it the other way around.
No, but if or, then we are doing it, then we are having more iterations.
The or and putting it outside and having or, and it will, if we have or, it's a bit faster because when the first one is 1, we expect that there will be a 1 in the line of the while. And if the first part of it is 1, maybe it's faster.
Yeah, we could try that. Let's maybe try, let's maybe start with this variant with, I think one idea was this might be true for a number of times in a row, especially if you have different lists of different, I think that's what I heard. Maybe we can also try your idea later. So let's do a while loop here. Let's do something like this. So while we are smaller in this list, let's just proceed in this list. But if we do that, then I think we have to introduce this again, right? And then we have to break, and then we have to do the same thing here. So basically we are back to the first one, except that we now have a while loop here. If J, B, and then, but now we again need this condition here.
But the condition should be in the loop, or we can run into...
Absolutely right. We also need, so the code becomes more complex now, it probably will be smaller, right? Because now we are going in this list more than once, so we also have to check, thank you very much for this. So we have to len B and this. We go here and then we might be at the end, we should stop. Now we know we are at the end of neither and we are here and now this is intersect. Variant with while loops to benefit from the case where we can skip larger segments in one list. Okay, let's try that. Let's first do the doc tests. Where was my doc test? Here we are. Okay, it still works. Let's do it again. 1, 200. This was not, now it's faster. Okay, So lesson, important lesson, you just wait and run it again. Then it's faster, probably something was happening on the machine. Still faster. Interesting, quite a bit faster, 3 times faster. And also interesting here, we made the code more complicated, right? This was much simpler, now we made it more complicated again, but actually faster. Okay, yeah, and interesting. Let's just, we could try out a lot, but maybe first. So I hear you talking, would be nice. Either you have to talk very, so avoid, yeah, let me do one very simple thing. Maybe in a language like C++ you won't need it, but let me just, I'm checking a lot against the length of A here, and I'm not sure whether Python will figure out that A actually does not change at all. I mean, a strict language like Java, C++, and so on will know this. Maybe it says here this is const, it will not change, then it knows that these len A are always the same number. Python might not be able to figure this out. So I think that's a very reasonable thing to try, to just give this a name here, and then we just, what do you think? Can Python figure this out or not? Will it make a difference? What's your guess?
Maybe it can look up the length in constant time.
Yeah, it can look up, exactly. So that's also a question. Maybe it can't figure it out, but it's so fast anyway that it doesn't matter.
We forgot to change in the docker.
Yes, that's very important. Otherwise, I'm not actually checking that this. So avoid evaluation, repeated evaluation of len A and len B, which don't change. So another very super simple, let's first check whether it's correct what we did. Yes, seems to be correct. Okay, let's do it again. That was our first one, 200 milliseconds, 120. We're down, okay, a little bit of variation. Still faster. Okay. Now here's a fifth fancy idea, and there are lots of ideas to have. Let's try, and then that's it for trying. Then I will try some other variations. Let's, what's one other annoying thing? I mean, we have dealt with this in all the variations here. You always have to check, am I at the end of one list? Am I at the end of one list? You have to do it here in the while loop. You have to do it here before we proceed. You have to do it again. You have to do it 4 times. One simple trick to avoid this is to put like special elements at the end. Avoid repeated check whether we are at the end of the list, whether we are at the end of one of the lists by adding a sentinel. So that's called a sentinel, so someone who's paying attention. It's just, let's just append infinity to the end of both lists, and you will see how a sentinel, infinity, in this case, it depends on the application, what the sentinel is. It's just like a special element which you insert, for example, in the end to avoid infinity. In this case, doesn't have to be infinity, depends on the algorithm, at the end of both lists. And let's just, and here we should change this to 5. Let's just see what, actually now let's just keep it for this while loop. And now what I'm doing, I'm just appending infinity here and to B. So what do I have now? At the end of both lists, I now have infinity, but after the last one, so I will not actually go there. And now I'm claiming that I can do this. So I don't have to check it in this while loop, because eventually, so I'm in this loop, which means none of the two lists have reached infinity, which is after the last element. And if one of the lists runs out, then one of these elements will be infinity and the other will not be, which means this loop will break, will stop eventually without overflowing, because there's infinity at the end, and I think I can do the same thing here. We still need this, because after the while loop, now we may be at the end of one of the lists, and so we should, but we don't have to do it in the while loop, so it's a rather small change. Now we have modified, and I think now we have to remove it again. So it's a bit ugly, because we are now in other languages where you would say, okay, A and B do not change, they are const, actually now they change, but just a little bit. So just appending inf, again the code becomes more complicated, but in a way that doesn't cost runtime, appending an element once and then removing it again. Is it correct? What do you think? Let's prove correctness. Prove correctness by running our doc test. So will it make a difference? Okay, this was wrong. That was our first one, 200 milliseconds. Our second variant, not quite twice faster. The third one, 3 times faster. The fourth one, 4 times faster. Still a little faster. It helped, it helped. So, we tried a lot of different things, more things to try. Small things didn't change the basic zipper, and we are 5 times, almost 5 times faster than what we started with, just in Python. Let's, yeah. And here are some things on the slide. I think you can read it yourself. Now, of course, the question is, why was it faster? Of course, if you yeah, I said it while we were trying these things, and but it's of course one thing to have an hypothesis, the other thing is whether that's really why it's faster. You would have to look at the actual machine code that's executed for understanding what's exactly the reason. But I think it's fair to assume that we removed code here in some cases. Less code was running, at least in the repetition parts. Variations in how the lists are stored. So Python has built-in lists which can hold any element of any type, so it's a pretty wasteful data structure, and it's also even not necessarily an array because you can insert something in the middle. So actually I don't know 100% how lists are implemented. I'm pretty sure that Python has an optimization that if you have a list which can hold anything and you can insert anything, but actually it just contains only integers and you never add something, then it's storing it in a more efficient fashion. I'm pretty sure it does that. But Python also has array, and actually I've implemented this, but I will just run it for you. So here is, yeah, and it's quite simple. It's just you import array, and all you do is here, if you look at this line, I'm just creating from my list an array, and I'm saying it's an array of integers. So I'm just telling Python, look, I'm only dealing with integers, please store it more compactly. And there's also NumPy, which everybody uses for all kinds of linear algebra. And yeah, let's just try it. Let's maybe not try all variations, but just the array, the first one maybe. Okay, so let's, this was the original one, and this is the array one. So if we use the more efficient data structure, it's slower. Let's also try NumPy, even slower. Okay, so you use array, the efficient built-in one, it's slower. You use NumPy, it's even slower. Interesting, right? So why is that? Actually, I think it's because list is optimized. It does something special for when everything is of the same type. But array shouldn't be slower, so that's a bit surprising. And NumPy is really not. NumPy is made for if you want to do linear algebra and special operations, like you have an array, give me the mean element of everything, or even do matrix multiplication, 2D arrays, then these operations will be implemented in C and very fast. But if you use a NumPy array and then you just loop over it, like we do here, that's a bad idea. I mean, you shouldn't do that. But it's something you have to know, right? So that's why I'm showing it. You might think, oh, NumPy is cool, everybody's using it, I'm also using it to get some performance benefit. No, you are not. You're getting performance penalty. Let's use PyPy. Who knows PyPy in the room? So PyPy is it's just a drop-in replacement for Python. You can just, and I mean, let's just do it. So here's our original program. And now I just use PyPy. Just instead of writing Python 3, I'm writing PyPy 3. Little bit of history, there are all kinds of projects, I think a dozen at least, which try to make Python faster. So there's Python, where you can write in your Python program C code. There is CPython, which tries to compile Python to C and then run the C code. There are ways to connect Python to C, integrate C in Python, integrate Python in C, with all kinds of native interfaces between the two. Quite messy. You're having to interface between two languages, writing that one language in the other. PyPy is you just write PyPy instead of Python and you install it before. And then hope that it's faster. And it's quite a bit faster. So it's quite amazing. How does it do that? And also interesting here, if I run it and I get funny effects here, which already give a hint at what it does. But you don't get these now the array is also fast, interesting when I do it with PyPy. Could talk a lot about PyPy. It does just-in-time compilation. It does not compile the whole thing and then run it, but while it's running it, it's seeing, okay, let me compile this loop body into C and then run it again. So that's why we have such effects. Loop body for the first time, it did some compilation and running it. For the second time, it just uses the already into C compiled body and runs it. So, and the great thing is so I wonder why not everybody you should always try PyPy. You have code, just run it with PyPy. If it works, maybe it's much faster. It doesn't work. It's a big project, and of all the projects I just named, maybe the biggest one. And their goal is to be almost fully compatible, which is very hard because Python has so many features. So some features in latest Python versions don't work, but a lot actually works. For example, Django, who knows Django, this web framework which is written in Python, some of you. And Django, you can just run it with PyPy, it works. So even big frameworks which use a lot of features and a lot of code, they work with PyPy. PyPy is written in R-Python, restricted Python, and the R-Python, so the code PyPy is is interpreted by code written in Python, and Python is compiled to C, so it's, let me look at the PyPy logo. Actually, I haven't looked at that's the PyPy logo. It's a snake eating itself because it's kind of recursive. Right? Written in R-Python, and the interpreter for that language in which PyPy is written, it's interpreted by Python. Yes. Yeah, and the improvement is enormous, right? It's a factor of almost 100 just by, and you might not even know this. So now let's do the real thing. Let's do it in C++. Just why C++ still a great language, in case you doubt that. We use a lot of C++ at our chair. I hear you talking. So C++ allows programming in a higher level language, type safety, nice abstractions, but the goal of C++ is to do it in a way, unlike Java, that you don't lose any performance, zero performance, compared to writing code in C or even a lower level language. And it does that pretty well, so you can always write very efficient C++ program. C++ syntax and concepts are a bit weird at times for the simple reason if something is around for a very long time and you have enormous amount of software written in C++, you have to be backwards compatible, not fully, but at least in important respects. Which means if you did a mistake in your language design 20 years ago, you're kind of stuck with it. You still have to support this stupid construct where you now realize, oh, I should have done this differently 20 years ago. That's always the problem with languages which are around for a long time. C++ does a pretty good job still. You have this bit clumsy syntax at times. Newer languages like Rust try to do that better, but of course they have the problem that they don't have this rich ecosystem. But, and I've written this for you, so we can just look at it together. For most code, it's actually not bad. This is the code for in C++. I mean, it looks very similar, right? I mean, now you have a parenthesis, unlike Python. You don't have a colon, but you have curly braces for the loop body. Otherwise, it's just, this is the if condition. It looks exactly the same. And let's just try it. Let's just run. And now, let's maybe, and then we are done with this part and we make a break. Let's just run it. And I think first we have to compile it. Yeah, let's compile it with nothing special here, so just standard optimization. The executable binary will be called intersect timing. Let's compile it, and now let's run it. So instead of calling an interpreter, I now do this and run it. Okay, that's too easy for C++. We have to go a little bit higher. Let's do that. Let's maybe start with a Python program, Python 3, and let's maybe just add a 0 here. Okay, now it's 10 million intersecting 10,000 with 10 million with our slowest algorithm. Okay, it takes 2 seconds. And now let's do the same thing with so what do you think? And now let's take variant 5 with the sentinels, 2 milliseconds.
What's the result size and why does it change?
It's because the random number generator is different. And also note, it's a different random number generator, so it's very hard to get the same random numbers for both lists. I would have had to do some special magic. This is just for consistency between the methods. Let's also compare it with PyPy again. And interesting thing, there are lots of interesting things here, so if you're interested in this, look at this again and try to savor all the little details. It's also pretty fast. Let's maybe also look at do you know how PyPy takes a pretty long time in the beginning? Even though it's much faster when doing the actual intersection, this beginning part is where it computes the random numbers, and a lot of them, 10 million of them. And it's not fast with that. So PyPy does not make everything faster. And the C++ code was actually also much faster in this initial part. So PyPy is not a secret source for everything. So we see PyPy gets a long way, but C++ is still 5 times faster, so, and a factor of 5. And actually you were right, maybe you were already peeking at the slides. So if we look at our slowest Python program, which wasn't so dumb, 2 seconds, and our fastest C++ program, 2 milliseconds, it's a factor of 1,000. And I think this is a really important message. I mean, this is definitely happening a lot. You have web frameworks out there which people use even for a lot of data, like our campus management system, I guess, is an example of that. And it's doing things 1,000 times slower, or even slower than that, than it could be possible by very simple changes. We are not even changing the algorithm here, right? This is all basic zipper. And now the following part will be about more sophisticated stuff. And also, so 1,000 times faster. with a simple algorithm, just algorithm engineering. So I think that's super interesting. So huge potential for performance gains, even if you don't change the algorithm, but you really have to understand what you're doing. There were so many effects here. Why was this slower? Why was it slower the first time? A lot you need to understand about the machine, about the programming language, about how the language maps to the machine code, and so on. So if you work with us, this is something we deeply care about, because we really want fast programs. So very interesting. And that was just a glimpse. And with that, I think we go into a 5-minute break now. And yeah, see you in 5 minutes. And then we continue with a better algorithm. So that was about engineering a basic algorithm and factor 1,000 differences. Now we talk about other and better algorithms. So the rest of the lecture is more theoretical, and also for a change the exercise sheet will be theoretical. I will talk more about that in a second. So just some preliminaries, just talking about technology. We always have two lists, just looking at the two lists case. And let's always call the smaller list A and the larger list B. They are both sorted. And let's call the number of elements in the smaller list K and the other N. So K is always less or equal to N. Let's maybe write that here. So K is less or equal to N. Of course, they could have equal size. Yeah. List intersection is commutative, doesn't matter A intersect B or B intersect A, so we can always just swap it so that A is the smaller list. And if they are equal, it does not matter which one is which. We denote the elements like so in array notation, so one based, because it's just simpler or clearer for explanation. So these are the elements of A. And for the following, always assume like few elements. When I draw a picture, I will just draw it. So we have, like in A, there are maybe 4 or 5 elements, and then we have B, this huge list. And they are denoted like this. And both lists are sorted, because otherwise you can't do things very efficiently. So we are just, but remember where they come from, inverted lists, they are sorted in the pre-computation. So we actually have these sorted lists. So the general idea of all the following algorithms, and I will have a progression of more and more complicated, not too complicated algorithm. You have the small list, and you try to, let me maybe draw a picture here and already show something. So I have my list A here, and it's just some elements, maybe 3 of them. So this here is my A of 1, and this is my A of 2. And by the way, in case you're noting that everything goes very smoothly here with the writing, Frank, who is not here right now, he did a lot of work he changed the whole setup basically. It's a new machine, because it turned out that the old machine, which wasn't so old, was just too slow for running Zoom, Camtasia and PowerPoint and stuff. So this apparently took quite a heavy toll on the machine, and now it's just a new machine with more power. Now we don't have these lagging problems. So what you want is, so you have this, and here you have the larger list, B, which I maybe just draw as a line because it's so many elements. And now what I want to find out, and both are sorted, I want to find out where does this fit in the list B, right? So here this would be index J1, and what it exactly means is written here. So this element A1 somewhere fits in the sorted order of B, between 2 elements of B, and the place where it fits just has a particular index J1. And of course the position of where they fit will be in ascending order, because both lists are sorted. So this might fit something here, so this second element of A might fit in here, and the third element of A might fit in here. So that's That's basically the picture you should have. What we are trying to do is we want to locate the elements of A in B, and when we have located them, so we know that the element just preceding this position here, the element in B is smaller, and afterwards it's larger or maybe equal. And now, if we want to do intersect, we can just check, okay, is it equal to the one before or after? And if yet, we output it. Yeah, and the details are not important now. You can read it later on the slide. These details are not important for what I'm going to explain. I just say it again. Just want to see where do the, in this case, 3 elements of A fit into B. And if you know where they fit in the sorted order, then it's easy to check, are they actually equal to this element of B or not, so to compute the intersection. Is there any question about this? Except about the details, which I glossed over now, but which are also not important. But that's the basic idea. Okay. So the first, you just do binary search. So let me just draw the picture again. I won't draw it too many times, but maybe this one time. So I have my list A with 3 elements, and I have my list B with a lot of elements. So here I have K in this kind, 3, and here I have N, some large number, maybe 1,000,000. And now I just want to see A, where's this first one in B? And I just do a binary search on B. How expensive is binary search of one element on B? Log N. It's log N, and I have to do it 3 times, K times, so the running time is K times log N. It's a very simple algorithm, not too bad actually. If I have a small k, if A is just one element, it's log n. If it's 3 elements, it's 3 times log n, still log n. So it's great for small k. If k becomes large, if k is on the order of n, then this becomes n log n eventually, right? So even if it's n half or n over 4 or something on the order of n, then this is not a good algorithm. It's actually slower than Zipper. But it's a good algorithm for small k. So let's elaborate on this idea. One obvious idea is, and that's pretty obvious. If you think about it, again, 3 elements, let's just do 3 for the sake of example. So our k is equal 3, and our b is some long list. And now let's assume we have already located this one here. So we know it's here. Then, and let me also, so this is the first element, this is the second element. Since these lists are sorted, it suffices to binary search in this range. Binary search A2 in this range. Right? We don't have to search before A1 anymore. Before A1 was smaller, and everything before A1 will be even smaller. I guess this is clear, right? I mean, you don't have to binary search the whole of B again, and of course it's good if at some point we find an element rather at the back of B, then the remaining range will be smaller and smaller. Let's just look, so it's a small optimization of the algorithm. What's the time complexity in the best case? Now? What's the time complexity in the best case? So you have k elements, and I want something with k and n. If you think about it for a little bit.
We need k steps. In the best case, we find them luckily from the first try.
Yeah, that's true. We even need, just k. Yeah, that's the very best case. That's true. It's not even the one I had in mind. Yeah, somehow by luck, the binary search just hits the element immediately. Ah, okay. But then you are in the middle, right? It's actually okay. So if you, then you are in the middle, and then you have to search the others in a, yeah. Okay, so there are, let me, actually, yeah, it's not so easy to see what the very best case is. So the somewhat best case, I would argue, is when the first element, and you find you do a full binary search once, and then you're already at the end of B. I mean, that's also your case. I'm not sure, because if the first binary search is successful immediately, then you are still in the middle of B, and you still have to search the second half or the second element. But you could argue that just after a few halvings, so maybe it's here in this end. So it's not not that easy to say what exactly the very best case is. But some quite good case is certainly when you find with one binary search, which takes log n, you're already at the end. So your A1 will be, and maybe we can just draw that here. So my B is like so, and let's just, and it's just to get intuition. Let's just say A1 is here. A1 is already at the end and nothing comes afterwards. I don't have to search anything for A2, A3 anymore, because I know that they won't occur in B. So it's basically one binary search. But that's, but maybe it could be even faster. But the point is, in the best case, this would be very fast. So what's the worst case complexity? So this is supposed to be an improvement of the previous one, which does k binary searches. What's the worst case? Yes? K, yeah, k log n, that's true. Yeah, it's k log n. Which, and when does it happen? Yeah, if it's the first, if all of them are, yeah, I think exactly, if all of them occur at the beginning of the list. And then you basically, it doesn't help you so much that you search in the remainder, because they are all, so A1, and then A2, they are all here, and A3. And the remainder of the list is always the whole list. Okay, and then we have, so this is k log n, so like in the k binary searches one. And then there's kind of the typical case, and the typical case looks like this. And let me maybe draw it here. Yeah, in the typical case, also in quotes here, it's like they are evenly distributed. Let's even say they're perfectly evenly distributed. So we have this here, and this here, and this here. And what's the running time then? If they're perfectly evenly distributed? Is it better, or is it, what do you think? So now, I mean, we could write it. It's actually not so easy, right? Let's start. So the first one is, you have the first one is log n. Now the second one is log n minus, if there are n over k, so it's searching in a little bit less. And the second one is log n minus 2 times n over k, something like this. And that's interesting, that's quite, so the, let me see whether writing at the bottom is always, the first k over 2 of these are still searching in a range more than half, right? If you just take the first half of A, they are still searching in more than half n over 2. They are still searching in more than n over 2 of B. It's a bit sloppy formulation. So yes, it becomes smaller and smaller, but the first k over the first half, you still search in half, so it's k over 2 times log n over 2. It's still k times log n. So asymptotically, it's actually not better. And that's quite typical. If you have something with log, it doesn't really help if it becomes smaller, but not rapidly smaller. So even in the typical case, yeah. Do you agree or do you disagree? Yeah?
What I'm wondering is now if the asymptotic case is identical,
Yeah.
but the searching in the remainder is a no-brainer, right? So how would you argue that the latter is better if the asymptotic complexity is identical?
Okay, so the question is, how would you argue that the latter is better if the asymptotic complexity is the same? Yeah, but that's this fundamental question about asymptotic complexity ignores constant factors, right? So an algorithm can be, if you take the first part of the lecture, it was the same linear time algorithms. Everything we saw was theta of n, just the size of the two lists, but there was runtime differences of a factor 1000. So in practice, it of course matters a lot, but so it's just two worlds. There's the asymptotic differences, where an algorithm can be asymptotically better, which is worth something, and then there are these hidden constant factors, which you ignore in the asymptotic analysis, but which are also very important in practice. So it's just two aspects, and both are important. And now we are in the theoretical part. We are trying to make it asymptotically better. So in practice, this would be better, but asymptotically, it's not better. Yes. Okay, so now let's try to make it asymptotically better. Let's try to do that. And here's an algorithm, and that will be the algorithm which you analyze for the exercise sheet. And it's doing something called galloping search. And it's a sequence of exponential and binary search. And let me just show it to you. Here it is on the slide. And I will not explain it to you in complete detail, because that is anyway something you only understand by yourself when you do it for yourself. But I will show you the basic idea, which is actually very simple. So let's again assume we have, doesn't really matter how many, 3 elements here. And now we want to locate them in the large list. And now, so I need a little more space here. Here's my large list. And let's assume I've already located let me draw the picture. I don't know, maybe I've already located my A1 here. It's here. J1, and now I know that my J2 is somewhere in the remaining part. So A2 will now be somewhere to the right of A1. So this is where A1 is located, and I want to find it, but I don't want to do a binary search in the whole part. So I first do an exponential search. So what do? Let me draw it like this. So this here is now position J1 plus 1. And this is position, this is a jump of 2. So this is now position J1 plus 2. And this is now 4, so hence exponential. So this is now position J1 plus 4. And this is now, not exponential, but let's just ignore this for now. J1 plus 8. Maybe let's go a little further here. Yeah. So I'm just probing B at positions which increase exponentially. So here it's written formally, so I'm starting from the position of the previous element I've located. I know my next element will be located on the right, and now I'm checking, is it located 1 to the right? Is it located 2 to the right, 4 to the right, 8 to the right? And when do I stop? I stop when, and that's written here. So I'm locating A2, right? I'm trying to find A2. Oh, actually I was using orange, so it should, yeah, orange, and this does not work at all. So my question is, where is A2 located here? And so what I'm probing at every position here, so here I find maybe that B, let me write it like this, that B at position J1 plus 1, I should write A first maybe. So I'm comparing the element A2 and so let's say A2 is still smaller than B at this first position. And I'm trying to find the first position where it's actually larger. So here A2 is also smaller than this one, B at position J1 plus 2. And it's also still smaller here. A2 is still... Am I doing it the right way around? No, this is where... What do I want to find? Do I want to find the first element where B is... is it wrong here or is it wrong here? I think it's...
That should be less than B, J.
Yeah. J1 plus 4. And then here I have... No, but this is wrong, right? It should be the... Yeah, so if I have... so I'm going, the elements of B are becoming larger and larger, right? So at some point my A is staying the same, so it should be... it should... I did it wrong here. Yeah, it's trivial, but it's easy to get confused about it when you're sitting right in front of it. So it's let's just, for the sake of example, it's always good to have a little example. Just a second. Let's just assume we have 70 here, we have 82 here, and 183 here, right? And now we are searching 82. So here it's element 17, and now we're seeing maybe 21, 35, 49, and here we are seeing 115 in B, right? So at some point, so my element in A, my 82, is larger. In just a second, I'm coming back to here. It's larger here, it's larger here, it's larger here, and at some point it will be actually smaller. And yes, there was a question, please, or comment?
Just from the figure, I assume the green arrows always originate at J1 and not from the previous point?
Yes. That's the way I... Yeah, it's actually, you can do it both ways, but it's inconsistent with what I wrote above. It doesn't matter which way you do it, the analysis works either way, because the sum of the powers of 2 is also essentially a power of 2, but you are completely right. So Yeah.
Shouldn't the equality be breaking condition?
Just a second. So I'm just wondering how I'm. Yeah. Let me just draw it differently. I mean, it should be consistent with what I did above. So let me just draw it like this, and then like this, and then like this, and like this. What was your comment?
So like, if the A is greater, then we move on. But if it's equal, then we stop. Right? So greater, and then.
I agree. You're completely right. Yes, these are also important details, also for your proof. If it's greater, if it's equal, I can already stop. So as long as it's greater, I still go on. And So I'm searching for 82, and I'm finding all these elements in B, which are still smaller, and then some point here I find. And now it's also consistent with what I wrote above. Yeah. So for example, let me just write examples here. So I'm searching for the 82, right? 82, and maybe here I'm finding, and here I have number 17 at position J1, maybe here I'm finding 21, here I'm finding 41, maybe here I'm finding 45, and here I'm finding 129 or something like this. So here for the first time I'm actually larger in B than the element I'm searching. And what do I know now? Now you can binary search here. Binary search in this range. Yeah, making mistakes, it's also good to understand something. Anyway, I think the idea becomes clear, so you're just probing at these selected positions which are at an exponentially increasing distance from the location of your previous element. At some point you find, okay, I know that my element I'm looking for is to the right of this, but it's to the left of this. And in this last range, and of course there is this border case where you're already past B now, then you're just searching the rest of the list, and now you're just doing a binary search here. So that's the basic algorithm, and now you're doing that for A2, and when you have located A2, you do the same for A3. Now you start from the position A2, you do the same thing, you jump in these exponentially increasing steps, and so that's the basic algorithm. Is there any question about the basic algorithm? And all the details, you have to look at them yourself anyway, because you have to prove something about this. And I haven't said it, but I hope it became clear just by talking about it. I mean, what's the point of all this? The point is that you want to avoid searching the whole remainder of the list, right? Let's assume that we would have been successful here already at J1 plus 4, right? Then I just have to search this range, and I don't have to search everything that's to the right of this. So I'm overshooting the ideal position a little bit. Of course, ideally, I want to find the right position right away, so I'm overshooting it just a little bit, but I'm overshooting it just by a factor of 2 at most. And this is something you can prove in the analysis. So that's the idea. Yes?
I'm not quite sure why this is asymptotically faster, because
Yeah, that's
in the worst case we have like the half of the space where we have to do the binary search, or am I thinking wrong? Because
So there are doubts whether this is asymptotically faster, and it's good that you have these doubts, because the proof is not at all trivial that it's asymptotic. The question is this faster? We have seen these progressions on the previous slide, where we tried things and they were not faster, so maybe this is also not faster. So you're completely right to ask this question, but it's a very hard question to answer, and it's not easy to answer it in any direction. And we will see it on the following slides. So it's actually quite complicated, which is what the rest of the lecture will be about. So it's a very reasonable question to ask, is this even faster asymptotically? So this is one claim. So what we will define, we will do the following, and let me again draw this little picture here. So we have the elements of A, and we have the elements of B. And now we have the positions in B where the elements of A are located. So here we have, let's say, J1, here is J2, and here's J3. These can be in any position. That's important now. We are not dealing with typical worst best case. They can all be at the front. They can be evenly distributed, all at the end, any position. And we're defining these DIs. And so this is just the gap between, so this is just the gap to where the first element is located. This is the gap from the first to the second, D2. And this is the gap from the second to the third. So these are crucial numbers for the following analysis. And what I'm claiming, and you have to prove it for the exercise sheet, but maybe you can get an intuition now, is when you're starting, and let me just go to the pointer again. Let's say I'm starting from here and I'm trying to find J3. I don't know where it is. Could be very close, could be very fast. And what I claim is that the previous algorithm finds this in log of this D3. Assuming D3 is not 0, then you don't have to do anything, right? So I'm assuming the DI are not 0 here. So finding this from here takes log DI. And why is that reasonable? Let's just say that you do a binary search in exactly this interval of length D3. That would take log D3, right? Let's just say you know that this third element is somewhere in this range, happens to be exactly to the right of it, then this would take log D3. Now assume you're searching in a range that's just twice as large, like log 2 of D3, right? So log 2 of D3, and that's just log D3 plus 1, which is also theta of log of D3, right? The log of something twice as large, if it's the, let's just take the log to the power of 2, it's the same for if you are in asymptotic notation, because it's just a constant factor difference. Just do it like this. So even if you're searching in a range that's twice as large as this D3, then it's still log the size of this range. And this is actually what the exponential search does. It will overshoot the real thing. So the real location of my A2 is somewhere in here. And by this algorithm, it will overshoot it by at most a factor of 2. So actually, that's why you will be able to prove this. And that's something you should do for the exercise sheet. So I could now do it all here, but experience shows that if I now also work out all the details for you, then you just don't understand it. You have to understand the basic idea. I think that became clear now. And now you have to try to prove this yourself, guided by the intuition I just gave. Was there another question? And of course you need to sit down and think a little about this. Yeah?
Why doesn't the y depend on the whole length of your array?
Doesn't the what depend on the whole length?
The
The y or the
dy.
di, you mean? Yeah?
Sorry, the di. Doesn't it depend on the whole on n?
Of n. So the question is, does this D3 depend on the whole of n?
Yes.
So the D3 is just a fixed number which depends on your input. So the J1, J2, J3 in my pictures are what you actually want in the end, but you don't know it yet. Right? So this is like for a fixed input, D1 may be 17, which means the first element is located at the 17th position of B. J2 might be 85, and J3 might be 215. And then these Ds are just the differences between them. So these are actual numbers determined by your input, but you don't know them. And this will be a topic on the next slide, which means your running time depends on some numbers which depend on the input, but you don't know what they are. But still, you can say the running time is log of some number. You don't know what it is, but it's well defined. It's a well-defined number. So that's a reasonable question. But we will see you can say something about this D1, D2, D3. Namely, so what's the total time complexity? It's just, so for every one of these searches you have a log of di, and you have to do something constant for each element also, just set of the search. So you have k plus the sum of these log di's. And that's what I just explained. I mean, it's not 0. Even if the di is 1, you have to do something constant for each element. That's why you need the k plus here. And now this addresses exactly your question. This is an unsatisfactory running time, right? It's k plus depending on some numbers, and I don't know what they are. It's numbers which are well defined, but I don't. And in particular, is this good or bad? I don't know, right? It's k plus some log of some di. Is this now better or worse than what we have seen before? We don't know. So, and you can prove, and you will also do the proof for the exercise sheet, that this sum is maximized. It's the largest, which means it's the worst. This algorithm has the worst running time if the elements are perfectly distributed over B, which means all the di are n over k. And this will be the last part of the lecture, will be about this, which means, so what this means is that, and you will prove it in the exercise sheet using a technique which I will explain in the last part. So you can prove that this sum here of this log di is less or equal. So actually this becomes largest, which means it's the worst case if all the di are n over k. So that's the worst case. That's the worst case, which means this running time is certainly log of n over k, and actually you need the 1 plus here, because otherwise this log of 0 is not defined. So that's just a technical detail, and you will 1 plus, because log 0 is not defined. There are all these little details here, but you really have to work these out yourself in the proof. The whole exercise sheet is just about understanding the algorithm and proving this yourself. It's not long proofs, but you have to understand something. So here we have these running times depending on these di, and I'm actually claiming the worst case, the algorithm is the worst when they are evenly distributed, and then I get this running time, and that's actually not a bad running time. That's now k times log something which is smaller than log n, right? Before we had k times log n, now it's k times log n over k. And actually there's also an exercise, I think I will skip these. These are just for, I think, let's just go to the exercise sheet before I explain to you, before another break, how you actually can prove this. So the exercises are split up a bit, but it's essentially the questions which were on the slide. So the first exercise is just prove that one step of this exponential binary search is exactly log of the gap, which you don't know, but it's still log of the gap. Then you prove that this is maximized for when the DI, when the elements are evenly spaced. And then the last exercise, it's also important, and I'm putting it all in the exercise, even this bound, is this even better than zipper? Is this better than linear? And is it better than k log n? This is the last exercise to show this. This is actually a very good bound. It's always better than linear, which is not obvious, but you prove it here. So it's better than k plus n, and sometimes even much smaller. I mean, let's just look for, let's maybe this one for node for constant k, for constant k. What is it for constant k? Then we have a constant here, and we have n divided by some constant. Log n divided by constant is still log n. The bound is now it's very quiet. The bound is O of log n. So yeah, it's actually, if you plug in k equals to 1, you just have log n here. If k equals to 2 is 2 times log n over 2. It's also log n. So it's actually a good bound. The question is, what happens if k becomes larger? Oh, this is sheaf, but that's how it is. If k becomes larger, it never becomes worse than linear. And this is the third exercise. So all the details of the analysis you're doing yourself. None of these are very big proofs or anything, but you have to understand what you're doing and work out the details yourself. Please also, this is a part here. If you have a great handwriting, this excludes most computer science students, I'm sorry to say. Maybe it has changed in the recent years. Climate is changing, maybe other things are changing too. I don't think so. You can also submit high-quality scan of high-quality handwriting. But if you are in doubt whether your handwriting is high quality, then the answer is no. Then you should just typeset it using Tech, which you have to do anyway at some later point in your studies. But if you have a nice handwriting, or you want to practice your handwriting, you can also. But two things. The scan has to be. So the worst thing is something terrible handwriting and then a terrible gray scan where you hardly see anything. Your tutor will have a terrible time. He will probably just, or she, reject it. So yeah, the default, I think, for most of you is just to typeset this. Do you have a question, or you were just stretching? Okay, so here just some additional information. I will not talk about it, just for your curiosity. And the last part of the lecture is about, and we will have another break, and then we will go there, is about this thing here. We have this funny time complexity of log of some values which we don't know, and I claim that the worst case is when the elements are evenly distributed. And to prove something like this, you need a technique called Lagrange Multipliers. Who knows Lagrange Multipliers? Have you seen them somewhere else? A few people have seen them. It's a very important technique. We will use it again in another lecture, which is why I will explain it to you today by an example. And we will do that in the last part after another 5-minute break. So see you again in 5 minutes, fresh for a final proof. We come to the fun part. Most fun, all the parts have been fun. This is now the greatest fun because it's mathematics, which you all love, I know it. Deep inside you, some maybe are not fully conscious of it yet. So Lagrange multipliers, they are for the following kinds of problems. You might not realize that this is the problem you have for one of the tasks which I've described earlier, but you will see it for the exercise sheet. It's finding the maximum value of a function under a certain constraint. And maybe I should, if it's too loud we have to close it, but let's try it for a second to give you a hint of why this is relevant. Where is, here we wanted to find the maximum value of this log di. And what's the constraint? The di, we don't know what the di are, but the constraint, they have a constraint, namely their sum is less or equal to n, right? Somehow these are the gaps between how the elements are located in D1, D2, D3, but they certainly sum to something less or equal to n. It can be less than n because the last element is not necessarily located at the end, so it's less or equal n. So you're asking yourself a question of the kind, this sum with these numbers, which are well defined, but which I don't know, what's the largest possible value of this under a certain constraint on the numbers? And that's exactly the kind of problem which Lagrange multipliers solve. And now here I have an equality, not an inequality. I have a slide about that. So you're asking the question, some function depending on several variables. So it was these gaps, d1, dk. Here it's just any variables, x1 to xn from the real numbers. I also have a slide, what about if they are just from a part of the real numbers, under a certain constraint, which is an equality. And I will just explain this method by an example now, and then you can practice it on the exercise sheet. We will have another application in the next lecture. There are some assumptions, I will go into the details here. These should be nice functions, which means when you compute the derivative, Ableitung, they are nice functions too. Partial derivatives, if you are afraid of partial derivatives, don't be afraid. It's just you take one variable and treat everything else as constant. So it's like the normal derivative. Yeah, so here are some conditions. I will not go into details. And what's the algorithm? So you want to find, like, where is this function the largest? You are constructing a function which is called the Lagrangian, after this famous mathematician Lagrange, where you just take the f function and the constraint function, you put them together. So it's just f plus or minus some lambda times the constraint function. That's what you do. We'll see it in a second. And now you compute all the partial derivatives of this function. So you derive by x1, x2, xn. You set it to 0. Now you get the systems of equations and you solve it. And now you know that the maximum you're looking for is at one of these solutions. Yeah? So you're basically reducing the problem to solving a system of equations, namely computing these n+1 partial derivatives, setting them to 0, finding the solutions, and then you just check at all these solutions what's the value of f, and you pick the largest one. And there are all these little details, they are mentioned on the slides, and you will encounter them when you do the exercise. That's like with a normal curve. If you only have one solution, you know it's a local optimum, but is it a minimum or a maximum? Well, if you only have one, then a simple way to check what it is you just compute some other point, right? And then if that other point is smaller, then you know that you have a maximum. If that other point is larger, the value, then you know you have a minimum. But it will be a maximum here and for the exercise sheet. Okay. And best way to explain such things, because it's really an algorithm, is by example. So assume we have a cuboid. This will, I think, take 5 to 10 minutes or so a little over time, but I think it's good to have this on the recording. So I have something like this, a box. Let me just draw a box here. And I have a side length. This is maybe x, this is y, and this is z, so they don't have to be equal. What's the volume of the box? X times y times z. What's the surface of the box? Well, it has xy twice here and at the bottom, so it's 2xy if I just want the surface. It has this one, this area here twice, which is yz, and it has another one which is, no, this is not yz. Yes, it is yz. And this is xz at the top. Is this correct, what I did? Yes, that's correct. Okay, and both of these I have twice. You don't see the ones opposite, so that's the surface. It doesn't really matter, it's just so that you have something to which you can imagine. So, and now I'm wondering, let's just say I have some amount of material, that's a typical toy example, some amount of cloth or something, 6 square meters, and now I want, and I can choose y, x, and z with a fixed surface, and I want to maximize the volume. How do I maximize the volume? So it's now a Lagrangian task. I want to find the maximal value for x, y, z when the surface has a fixed size. And note here this little transformation that I did. So my surface, I said it's 6 square meters, and let me just drop there. So it's 2xy plus 2xz plus 2yz is equal to 6. Well, I can divide it by 2. xy plus xz plus yz is equal to 3. And I just can make it into something equals to 0 by just bringing the 3 over here. Because for Lagrange you need a function which is 0 at the... So and that's just how I define my g here, right? And I can of course always do that. That's just how I define my g, x, y, z. So that way I now have it in the form of a Lagrange multiplier exercise. So I want to maximize x, y, z, the volume under this constraint, that this function g is 0, which means the surface exactly 6 square meter. Check the assumptions. We will not do it here. You can check it yourself if you're interested. If I just take the derivatives of, these are all very smooth functions, partial derivative of this by x, so x is treated as the variable, y and z as constants, it's yz. These are the other partial derivatives. This is continuous, fine. If I compute the partial derivatives of g, I get this function, which is never 0, at least not where the constraint is fulfilled. You can check it. This is also something you have to check for the exercise sheet. It's just that the assumptions which I've written earlier on the slide are fulfilled. They are fulfilled here. And now let's do the actual thing. This is also what you have to do for a different function, of course, for the exercise sheet. Now we will just compute. We have this Lagrangian, which is just the volume minus lambda times the side constraint, and now let's just compute the partial derivatives. So by x, which means my x is now the variable, and y and z are constants. You could imagine numbers here, like x times 7 times 5, right? And if I derive by f, it would be 7 times 5, 35. So it's like, this is y, z, minus, and now I derive by x, so here I get lambda y, then I get minus lambda xz, I derive by x, it's lambda z, and if I derive yz by x, it's like a constant, it disappears, 3 disappears, yes. And this is 0. So I do this equation system. And now, and you check please whether I'm not making any mistakes. Let me just write all the, this is now x, z, minus by y, lambda x, minus lambda z. This should also be 0. Let me compute the derivative with respect to z. So it's not really hard, it's computing derivatives. This is x, y minus lambda x minus lambda y equals to 0. And then I also have to compute the derivative with respect to lambda. And if I compute the derivative with respect to lambda, this disappears, there's no lambda. This lambda is the variable, and I get this here remains. This is a constant, which means I get xy plus xz, and this is no coincidence, it's always like this. I get exactly the side constraint. So setting the derivative by lambda to 0 just gives me the side constraint. It's just by the way how this L was constructed. Okay, let's just, and now we try to solve the systems of equations. I mean, maybe do it a little bit quicker. And this is now typical mathematics exercise. How do you solve? It's actually a nonlinear system of equations. You have products of the variables. How do I solve this? Let me just, let's just put 1 and 2 together. I hear you talking. You can ask a question if you like.
Just thought about when we do the derivative of lambda, it shouldn't be a minus in front of everything because of minus lambda.
The same thing.
You are absolutely right, but of course it's the same thing because I'm setting it to 0, but as I wrote it here, it's wrong. Yes, you're completely right. So I should write it like this. And then of course I can get rid of the minus, but you're right. This is not the derivative, it's minus the derivative. Let's just take these two together, 1 and 2. What do I have? If I just subtract them from each other, I get, I think, x. Let's just take 2 minus I. So I subtract this from this, then I get x minus y times z is equal to, and then I think it's, I think I get this x minus y times lambda. Is this correct? I think it is. So if I just, if I just subtract them from each other, I get, this disappears, lambda z is in both of them. Yeah, if I just combine these two, I get this. And this, well, what does this mean? And I mean, I won't go, this is just solving a systems of equations by some creative idea. When does this happen? When is x minus y times z equals to x minus y times y? It either happens when x is equal to y, right? Then it's 0 here, and it doesn't matter what z or lambda is, or if they are not equal, z is equal to lambda. And I think similarly you get I think you get 2 more constraints. You get x is equal to z by just combining 1 and 3 and 2 and 3. You get x equals to z or y equals to lambda, and you also get y equals to z or x is equal to lambda. And I don't think I will finish this in all details now, because you can do it as an exercise, or you just do it as there's only one solution here. It's a bit more fiddling around, but not much more. The only solution this has is x, y, z. I mean, there's already a lot of equality here. If you think about it a little more, there's only one solution. The only way these equations can all be 0 is when x, y, and z are all equal. There's a lot of symmetry here, so it's not too surprising. If x, y, and z is all equal, then what is lambda? We can derive this here. This is then y square minus 2 lambda y square, and lambda is 1/2. But the value of lambda is actually not important at all. It's just a variable here in the mix. What you are interested is x, y, z, and that's the only solution. So in this case we have only one solution. There could be several. Only solution. And so I think so our only solution was, so what was our f? We were computing the volume, x, y, z, and our g of x was this xy plus yz plus xz minus 3. Yeah, and so our solution was and I think we didn't really compute the value of we can do it here. I mean, if they are all the same and this constraint has to be satisfied, what are actually the values of x, y, and z? This we can do because it's easy. You know that they are all equal and g, the constraint g, is satisfied. Then what's the value of x, y, and z? There's only one answer. 1, yeah. Because g, x, y, z has to be 0. X, y, z is equal to 1. Okay, and then we have f x, y, z is 1. So the answer is that, which is maybe not so surprising, you could probably have guessed it, if you have a fixed surface and you want to maximize the volume, then a cube is the optimal solution. And this is the way to prove it. It's actually not so easy. You need this technique. So you have something under a certain constraint, that's the way to prove it. So the cube is, if you want to maximize the volume, makes sense because if you do something, I mean, otherwise it happens at the cube where everything is equal, or it happens at the border cases where it's a very long box or something, and when you have a very long box, then one of the edges becomes 0 and the volume becomes 0. So maybe not so surprising. Okay, this is just let me mention it very quickly and then we are done. Lagrange actually wants the side constraint to be an equality, but what if we say it's an inequality? So I'm saying maximize the volume under the constraint that the surface is at most 6. And you can't directly apply Lagrange, but there's a very simple trick. You just say, okay, so it's something not 6, but something that's less than 6, just give it a name, S, then do Lagrange with this equation, and then just look at the end, okay, when does this whole thing get maximal? And of course, to maximize the volume, you should also maximize the surface. So first you get a solution in terms of S, and then you wonder, when is this maximal? Well, it's maximal when S is 6 in this case. So yeah, the same trick also works it almost works. And there's just a little detail in case you stumble across it. So in my definition, I assumed that all the numbers were from all the real numbers. This also includes negative values in this case. So my edge length could have been negative. I mean, this I can still compute. It's not a volume then, but I can still compute it. But in this case, it didn't harm because the maximum occurred at a positive values. For the exercise sheet, it's a little more complicated because your numbers, this di must not be negative because you have the logarithm of them, and you can just ignore it. You can just ignore that everything is, that you can still do Lagrange even though you're restricting your numbers to be non-negative. So that's it for today. The exercise sheet, I explained it to you. Is there any question right now? If you have trouble, please start working on it early. So it's just these math tasks, which are basically one bigger math task. If you have a question, ask on the forum. Try to ask in a way that we can help you. Is there any question right now? So thank you for your patience. Have fun with the sheet. See you next week.